In this video, we will continue our investigation into several examples involving the common antidifferentiation formulas along with the method of substitution. So to begin, we'd like to evaluate the given integral. Now the observation I'm going to make is because of the x times the square root of x plus 2, algebraically there's really no simplification that allows me to break this up in any meaningful type of way. And that only leaves me with the possibility of doing a substitution. And when performing a substitution, what we'd like to do is pick u to be something inside another function, and typically the largest possible inside function. So the choice that leaves me with would be u is equal to x plus 2, which makes du equal to dx. And what we need to do is take our integral solely involving x's and get it back in terms of an integral only involving u's. We have this kind of pesky leftover x. And if you ever have leftover x's that you need to get in terms of u, we go back to our substitution. The substitution gives us the relationship between those two variables. So u minus 2 is equal to x. So we can replace this x with u minus 2. So an equivalent indefinite integral in terms of u, we would have u minus 2 times u du. And this really is our ideal position because we have everything in terms of powers of u. So what we can do is go ahead and take this square root of u, think of it as u to the 1/2, and distribute it through. So this becomes the indefinite integral u to the 3/2 minus 2u to the 1/2. And we can antidifferentiate each term individually. So 2/5 u to the 5/2 minus 2 times 2/3 u to the 3/2 plus c. And for an indefinite integral with a u substitution, we finish by resubstituting. So each of the u's get replaced with an x plus 2. Which completes the integral. So let's look at another example. And the thought process is the same here. I look at the integral and I think, can I immediately compare this to my table of common antiderivatives or get there through some algebraic simplification? And here the answer is no, which means I should be thinking about a substitution. And looking at the form of the integral, this sine squared, remember that an equivalent way to write sine squared would be sine of x, quantity raised to the second power. So that really indicates to us this inside function u. So we can let u be equal to sine of x, so that du is cosine x dx. So this really is the ideal situation. We very quickly can convert this entirely in terms of u's, and not only that, the resulting integral is very quick, very efficient to evaluate. And then resubstitute back in. So as a reminder, if you look at the integral, and as we saw here, we cannot directly compare this to anything in our table, look for now for those kind of maybe more obvious substitutions. What can I let u equal to? And then give it a try. So let's evaluate the given integral. Once again, especially because of this t out front, I can't compare it directly to our table of antiderivatives. There's no obvious algebraic simplifications, but there is this inside function that could certainly play the role of u for a substitution. So if we let u be equal to 3t squared, note things are going to work out nicely because when you differentiate a quadratic, you get back a linear. So we have 6t dt. We have a t dt in our integral, so dividing by 6, 1/6 du is equal to t dt. So once again, the integral may look a bit difficult to get started, But once we see the substitution, it very quickly turns into a reasonable integral. The antiderivative of e to the u is simply e to the u. And then we resubstitute in that u is 3t squared. So one more example for us to evaluate, this time a definite integral. Upon inspection, very similar to the previous example, we see that we have the square root inside the exponential, and we'll say up to a constant, its derivative is appearing outside. So what we're going to do is try a u substitution with u equals the square root of x. The derivative of the square root of x is 1 over 2 square roots of x. So what we have left over in our integrand is not quite du, but if we multiply by 2, we would get du from it. So we can take our integrand and very nicely convert it in terms of u. We have a 2 that pulls out front, and then we would be integrating e to the u du. But as a reminder, because it is a definite integral, we need to switch our limits of integration. So we need to get our new limits. So we think, okay, when our lower limit, when x is 1, what is that corresponding value of u? And to change the limits of integration, you always go back to the substitution. When x is 1, u is the square root of 1, which is 1. So our lower limit of integration is 1. For the upper limit, we think when x is 4, what is u equal to? When x is 4, u is the square root of 4, which is 2, so our upper limit of integration is 2. Now the really nice thing is that since we've switched our limits of integration, we have an equivalent integral in terms of u, and once we evaluate this definite integral, we get back a number, and that number corresponds to the value of the original definite integral. So we antidifferentiate e to the u, and we evaluate with the fundamental theorem of calculus. So we plug in 2, we put a minus sign, we plug in 1. And if you want to simplify this ever so slightly, say a 2e is common to both terms. When you pull that out, you're left over with an e minus 1.